Okay, so in our first question, we have a tension of 8,000 newtons, so I'll do A over here. So my total mass is 570 kilograms. The force up is 8,000 newtons. The force down must be 570 G. Okay, we can eyeball this and see that it's going to accelerate upwards. To work this out, 8,000 minus 570 G equals 570 A. This gives me 8,000 minus 5586 newtons, and if I subtract these two and then divide by 570, I get the answer of 4.24. Okay, to find the reaction force, which is, remember, this force here at the base of the lift, okay, this reaction force because of this chap's weight, I zoom in. Okay, so if I just look at the base of the lift here, the force of the man down is 70 G. The reaction force, Rn, must be more than 70 G because we're accelerating upwards. So I write Rn minus 70 G, and that equals 70 A. Now I know what A is, it's the same for the man and the lift, so I do Rn equals 70 times by 4.24 plus 70 G. So crucially, he's going to be heavier than if it was at rest. And if we work this through, we get a value of 982.5 newtons. Okay, for part B, it's going to be a very similar method. Again, start with our total lift and person combined, so 570. The tension upwards is 3,000 newtons. The weight down is still 570 G. In this case, again, if you eyeball it, you can see it's going to accelerate downwards. If you're ever concerned about which way A is going to go, just see which force is bigger. You can tell after a while which one's going to be bigger, but if you're not sure, just work it out, times by G, work out which force is bigger. So in this case, it's going to be 570 that's bigger than 3,000. And if I work this through, again, I get 5586 minus 3,000. Divide through by 570, and I get 4.54. Okay, and it's important that you know that that's down. Okay, you know which direction that's in. The question I've written hasn't been prescriptive in how you do that, but the acceleration of the lift is 4.54, and we know that it's going down. You get away with putting minus 4.54 if we consider up to be positive. But yeah, the second part, again, our reaction normal force is here, 70 G down. Which one's bigger? Well, it's accelerating downwards, so 70 G must be bigger than Rn. So if I put Rn on this side, I have 70 G minus 70 A. So Rn is going to be 70 G, subtract 70 times by 4.54. And that gives me an overall answer of 368, sorry, 0.2 newtons. Okay, so two questions very different. This one we're accelerating upwards, so our reaction normal is more, so we're heavier. In this case, we're accelerating downwards, so our reaction normal or our weight is less. Okay, again, remember, look at the big picture, zoom out, then zoom in for the second part of the question. So part A of this question, we're told that the whole system, which has a mass of 260 kilograms, is accelerating upwards at 2 meters per second. Okay, so the force downwards is 260 G. Therefore, we can work out what the tension in the cable is. So it's going upwards, so it must be T minus 260 G equals 260 A. We know that A is 2, so let's make that 520. So our T value is 520 newtons plus 260 times G, the weight of the person and the lift. So when I add these together, I get 3,068 newtons. There we go. Okay, so the man in the lift, well, let's look at the reaction force. We have 60 G going down, we have Rn going up. It's going upwards, so it must be Rn minus 60 G, and that equals 60 A. Remember that our acceleration is still 2, so this is 120. And to find Rn, I add the 60 G to the right-hand side. So I get 120 plus 60 G, and that gives me a value of 708 newtons. Remember, as a general rule, if we're accelerating upwards, we're going to increase that normal reaction force. Okay, part B, start off in very much the same way. The birds are making an absolute racket this evening. 260 kilograms, T upwards, 260 G downwards. In this case, we're going this way. So I write 260 G minus T equals 260 A. Let's move this around. So we end up with T equals 260 G minus 520. Remember that this becomes 520 because our acceleration is 2. So this gives me a tension, 260 minus 520 of 2,028 newtons. Okay, final part, our reaction normal. 60 G down again, Rn up. We're going downwards, so it's 60 G minus Rn, and that equals 60 A. Rearrange it again. We add the Rn over, take away the 60A from the 60G, so we have 60G minus 60A, which is of course minus 120. So 60G minus 120 gives me a reaction normal on the floor of the lift of 468 newtons. Okay, so slightly different this time. We're going to work from the normal reaction force backwards. So let's start with A over here. So in each case, we are started zoomed in. So we have our reaction normal, 100 kilograms. And so in the first case, we're going to use the reaction normal and the weight of the passenger in order to find the acceleration. So we're told that it's 1,470, so let's start with that. So 1,470 minus 100G, 980 newtons, and that equals 100A. Okay, so we end up, if we do 1,470 minus 980, we have 490. Therefore, my acceleration is 4.9. This way I'll put a little arrow on that it's going upwards. Okay, so we want to find the tension and the acceleration. We've done the acceleration, we want to find the tension in the cable. So for the whole system, it's going to be T minus the total weight downwards, and the total weight downwards is going to be 950 G, and that equals 950 A. Now we know that A is 4.9, so it's 950 times by 4.9. So T is going to equal this 950 times 4.9 plus 950G, because it's raising that weight as well. Okay, so that gives me a T value, big number, of 13,965 newtons. Okay, question B. Start again, zoomed in. Rn this way, 100G this way. In this case, we have 645G. Now we know from our previous workings that means it's going to be accelerating downwards. So we start with 100G minus 645, and that equals my 100A again. Okay, so it's going to be 980 minus 645, which gives us 335. So our acceleration is 3.35 downwards. Okay, again, thinking about the whole system, we have 950G downwards, which is the weight of the whole system, minus our tension, and that's going to equal 950 multiplied by 3.35. So T, if we rearrange it, is going to be 950G minus this 950 times by our acceleration. And this gives me an answer of 6,127.5. Great. Okay, last one then, C. So let's draw out again. Hopefully we'll notice something about this very quickly. I have 980 newtons down. Upwards I have 980 newtons. Okay, well this means one thing. It means the acceleration must be 0. Either we're stationary or we are moving at a constant speed, so Newton's first law. Okay, just to show you this, we do 980 minus 980 equals 100A. 100A equals 0, so A equals 0. You don't really need to work it out. You can see that straight away. And if this is true, then the tension must be equal to the entire force downwards. So the entire force down is 950G. Therefore, the tension must equal in newtons 9,310. Okay, so if we look at the first question here, we have this 5 meters upwards, and we want to find the 3 forces. So I've labelled them on here. We have RBA, RBC, and RCF. So BA is the force of B on A, BC is the force of C on B, and then CF is the force of the floor on C. Now, the thing that's important to realise is that, for example, if I'm at this point at the base of B, I've got the weight of A and B combined above it. So what I'm going to do is I'm going to show you how to do the first one, and then I'll show you the rest of them kind of in a bit of shorthand. So for the first one, if we're going upwards, I'm going to have RBA going upwards, and downwards I'm going to have the weight of 25G. Okay, and that's going to equal 25A. So if I rearrange this, I get RBA equals 25A plus 25G. Now, this becomes 25 times by 5 plus 25G. Okay, so this gives me a value, when I work out, of 370 newtons. Now I can do the same thing for the rest of them. I can say that RBC must be 85, because we have 25 plus 60, so 85 times 5 plus 85G. And this gives me 1,258 newtons. Finally, I have RCF. And in this case, the mass above it is 205. So it's 205 times 5 plus 205 times G. And this gives me a value of 3,034 newtons. Okay, so that's A all sorted. So for B, I'm going 3 meters per second downwards. Okay, so if I look at the first one, look at RBA, I'm going to have 25G minus RBA equals 25A. And if I rearrange this, I get 25G minus 25A. So when I work that through, I get 25G minus 25 times by 3. And that gives me a value of 170 newtons. I can do exactly the same for the next two. So I have RBC. In this case, it's going to be 85G minus 85 times by 3, the acceleration. And that gives me 578 newtons. And finally, I have RCF, which is 205G minus 205 times by 3. And that gives me 1,394. Okay, so in each case, you need to think to yourself, if I choose a point, say I choose this point here, what weight is above it? In this case, 25G. So I work from there. If I'm right at the bottom here, for example, I need to think about the 3 masses above it and their combined weight downwards. Okay, but in each case, just think about that interaction between the block and the block below. And yeah, you should be able to get used to this sort of method. Okay, so for the start of this question, we can go back to our connected particles on a pulley idea. So we're going to create an equation for each one of these. So if I label on the forces to start with, I have 50G here and tension upwards. This side, tension upwards, and this whole particle down is 7G. So the equations we're going to write, 50G minus T equals 50A, and T minus 7G equals 7A. If I combine the left-hand side, I get 43G. On the right-hand side, I have 57A. So my acceleration is going to be 43G divided by 57. This gives me a value of 7.4 ms to the minus 2. The tension, if I put it back in to the bottom equation, actually just put in the top equation, I have 50G minus 50A. So I have 50 times 9.8, subtract 50 times 7.4, and I get a value for the tension of 120.3 newtons. Okay, moving on to question C. The reaction in the lift. Well, we know that the lift is has no mass. The only mass in this whole particle is the 7G. So the weight down is 7G. And what we'll notice, if I write this, Rn minus 7G equals 7A, is that this looks very, very similar to this equation here. Now the reason for that is that there's no other mass on this particle. Okay, so actually we have the same equation, which means that Rn, when I put my figures in, I have 7 times 9.8 and 7 times 7.4. My reaction normal is the same value as the tension. Now the reason for that is that there's no mass for the lift, so this situation is basically the same as having this cable attached to this mass directly. Okay, so there's plenty of really good explanations for this online you can find. I would have just go on YouTube and see if you can find a good one. Hopefully when you looked at this, you realise it's a bit of a weird idea. But what I'll kind of think about with you is that two different sort of concepts. One is if I'm in the lift and unfortunately I am falling, let's say in the first instance, we've got to a sort of terminal velocity, so there's no more acceleration downwards. Now, if we're in constant velocity, would I be able to jump up in the air? Yes, I would, absolutely, because your weight and the normal reaction force will be balanced. So you'll be able to jump, but all that's going to happen is you're going to jump up and then land again. You're not going to jump up and float. There's no sort of weightlessness going on. So you're just going to jump up, land again, and it's going to be very uneventful. It won't help because when you land, you're either going to be in the air or you're going to have your feet on the ground. Now, either way, when the elevator collides with the floor, you're going to hit the floor, okay? And you're going to take that impact and it's going to be bad. Now, so it's not going to help you at all, no. It's mathematically invalid, it's not going to help at all. You're still going to be in contact with the floor and you'll hit the bottom of the lift, okay? So that doesn't work. The second situation, which is maybe a little bit more interesting, is if you are accelerating. Okay, now the constant velocity is an interesting one. Yeah, you probably won't get to a constant velocity, but if you're accelerating at the maximum possible, so that'll be gravity. Now, if you're accelerating downwards at gravity, let's have a think about this. So say your weight was 60 kilograms. Your weight down is going to be 60g, and your reaction normal is going to be this way. So what we need to think about is, well, what is your reaction normal going to be? Now, hopefully it's obvious. If I just model it as Rn, I don't know, plus 60g equals 60a, and I know that a is 9.8, I get this 60g equals 60g, therefore Rn must equal 0. So you will feel weightless. Okay, you'll feel weightless. Now, the issue with this is, are you going to be able to jump? And the answer is, no, you're not. Because if you feel completely weightless, if there's absolutely no reaction force, you're not going to be able to provide any extra force to jump. So if you're accelerating downwards at gravity, you cannot jump because jumping requires you putting extra force into the floor of the lift. So if you're accelerating like this, you cannot jump. So this is impossible. So if you're going at a constant speed, yes, you can jump. Will it help you? No. If you're accelerating at 9.8, can you jump? No. Is it going to help you? No, definitely not. The biggest problem with this idea, and I don't know why it's such a common idea, but I think the idea is that you think if you jump, you end up floating, I guess, and then you come to a nice gentle rest at the bottom. That's obviously ridiculous. So hopefully you can see that. The main problem with this is lifts do not have glass floors. So how are you going to time your jump to when you're going to hit the floor? Well, you can't and you won't, and it's not going to help you anyway. So if this happens, which by the way, it can't happen, the reason it can't happen is because lifts have several cables. So if one snaps, you're still fine. So this can't happen. Bit of a ridiculous question, isn't it? So it can't happen, it won't happen, jumping's not going to help, you can't jump, and it won't happen anyway. So there you go. The end.